Right. Hello, everyone. So, the current lecture is the continuation of the whole vibration lecture series, both in recorded form as well as in the live classes. So, if I'll just quickly go through the today's topic, it will be like we have seen, we have discussed most of the topics in vibration, and we are doing this in continuous form. So today we'll be discussing simple and compound pendulum. So this is a kind of very repetitive topic in our gate, and many questions are asked related on this topic. It's a good conceptual topic. So we'll focus on pendulums today. So before giving you the solution, just keep one thing in mind. I'm focusing on these kind of things. Maybe you people will understand. So there is a rope kind of thing on which a bob is suspended of some mass m. You know, this is a pendulum. This will vibrate or oscillate like this to and fro motion. The another case which I want to take is that in place of rope, you have a rod of mass M, and this rod is vibrating like this. So it becomes kind of a pendulum now. And the worst case scenario, in which you have a very arbitrary shape, and we usually use the word compound pendulum for this, and this pendulum rotates in this case. And as we are in vibration, so keep this in mind for all the three cases, or for any of the numerical, not only pendulum, for any of the numerical, we always focus on calculating the natural frequency of the system, all right, which we refer to as omega n. You know the physical significance, we have already seen this. So this is how uh, the system will look like, and that's what we want to do. So there are few questions I have kept it here, like a rod of some mass and so I will take help of this numerical, this question. I'll explain you the concept. We'll try to complicate this simple problem into a compound pendulum, and then once you know the worst concept, then we'll try to move on to the first case, which is very simple pendulum, which you have seen up till now in throughout the textbooks. So it's something like this, guys. I'll take this to the next slide, and then I'll show you what we are trying to do. So you have a hinge point here through which, if you see, a rod is suspended and it is being given a displacement. So this is the mean position, and you have a rod of mass M and length L. All right, length L is suspended. It is given a displacement theta, and we need to calculate the natural frequency of the system. All right. So very few basics. So maybe some of you are only seeing this video. So just for those people, when we say vibration, when we say natural frequency, the only thing we need to keep in our mind is we need to write the equations of motion. Now, when you write equation of motion in simple words, it tells you how your system will going to move with respect to time. That's what the catchy word of equations of motion meaning is, what it tells you. And before that, we should know the degree of freedom. So I'm not going into detailed explanation of what is degree of freedom and how it is defined. But in simple case, if you see this, there is a rod which will rotate like this only. So the only motion, if I want to explain it, is if the rod is here straight, I'll say theta equals to 0. If rod is here, let's say maybe theta is 45. So the only thing to required to define the system, to tell you the location of the rod, is only theta, and hence the degree of freedom for this system is 1. So it has only one equation of motion. Now, there are multiple methods in vibration which can give you. There is energy method, there is a Rayleigh method, there is a Newton's method. So I'm giving you the easiest shortcut method, and it is the best method for capturing your vibration problems. Let's see how it works. So I'm basically going for Newton's method. So the first thing I want you to understand and make it very clear in your mind is, whenever you have a system which is rotating, so you don't have inertial force, you have movement terms present. Now, what do you mean by this? Assume that you don't know anything about vibration, and then you listen to this lecture. All right. So first thing, when you see a system, the first thing you need to decide is this system having a translation motion or a rotation. Now, what do you mean by translation motion? I'll give you a simple example. Let's say you have a system like this, and this system mass moves in this direction and comes back in this direction. So this is to and fro motion, translation. This is translation motion. Right? There is no rotation of the mass here. This is what I'm saying is translation mass. And the inertial term in this case is mx double dot. This is inertial force. Mass into acceleration is a force term, which should always come in your expressions if there is a translation motion. But if you see precisely in our problem now of pendulum, there is no one moving forward and backward. There is rotation of the system. Whenever you have a rotation of the system, you don't have inertial forces, you have inertial movements. Now, I'm again repeating this. We have discussed this in great detail in the previous lectures. What do you mean by inertial force? What do you mean by inertial movement? But even if you're starting from scratch, I hope you should take this as a rule as of now and start solving these kind of bad numericals. It can solve anything once you know this concept. So the term which I'm saying is I theta double dot. So guys, this is very, very much similar to mx double dot, but the only difference is here mass will move front and back, to and fro, translation motion. When the same mass rotates, you have I theta double dot term. So this is force and this is movement term. You will come to know why this is movement term. So whenever there is a system in which there is a rotation, close your eyes blindly, simply write I theta double dot. I'll tell you how to play with this term later. So first term is fixed. Now the second term is this, guys. Now you need to understand a bit. So in this diagram, I'll try to make it a bit clean so that I can draw some diagrams in this. So diagram is, if you see this rod is having CG about its own center. Correct, right? It will be about its own center. It's a symmetric rod of length L. Nothing is mentioned. And at CG, there will be a weight which is acting downwards. Always this weight will act downwards. Now, if you see, with respect to vertical, this angle will be theta. All right. And this angle, if you resolve, this will become W cos theta here. And this will become W sin theta here. I'm assuming that this is clear. If we have doubt, we can definitely have more discussions on this. That's not a problem. All right, I'll take doubts in the end ways. So you have a weight acting downwards, cos component acting along the axis of the rod, vertical or the perpendicular component W sin theta acting perpendicular to the rod. Now, if you listen to the statement now, when you're using Newton's method, this I theta double dot term, always we are writing everything about the point of rotation. And I am very, very much clear, rotation is about this hinge point. The whole system is rotating about hinge point. So identify the point of rotation. If you know the point of rotation is hinge point, perfectly fine. Now take movement about this term. This I theta double dot, I will explain this later what this physically means. This is about hinge point. This inertia will be about hinge point. The next term is, if you see this W cos theta term, this will not create any movement as it is passing through this hinge point. So this will not come into picture. But if you see this W sin theta, and because this is acting at CG, the half distance of this will be L by 2. So it will create a movement W sin theta into L by 2. I told you, right? Whenever there is a rotation, all these are movement terms. So what you blindly need to do is you just need to take movement about the point of rotation. First, write I theta double dot term. Don't worry about it much. And then whatever force is present in the system, that force should create a movement about that hinge point. If it is creating, write it. If it is not creating, make it as 0. So I'm not writing W cos theta. I have written W sin theta into L by 2. Now the next point is this. How to decide plus and minus? All right, so the easiest thing is any force or movement which bring your system back to equilibrium is known as a restoring movement. This is restoring movement. I'll give you the example of the other one. This is restoring movement. The reason being, this force, if you see, when this pendulum goes to this side, this W sin theta term is bringing it back. This is the reason I'm using the word restoring movement. Now, For example, if you have a spring and you have a mass connected here, when this mass goes to this side, this spring will bring it back. So this is restoring force now. And I hope most of you have seen plus kx term equals to, let's say, 0 or something. I'm not interested in that. So whenever you have a plus sign in the terms, right, that means it is bringing your system back. It is restoring your system back. If there is a system which is overturning your system, it is taking your system further away from equilibrium. I'll give you the example later. Then that is referred to as overturning force or overturning moment. I'll come to that. So if you see in the system, you have considered the inertial term. You have considered the inertial term. You have considered W sine theta into L by 2 term. W cos theta is not doing anything. And I'm talking simply about calculating the natural frequency. So I'm not considering any damping. I'm not considering any force of the system. And hence, the equation turns out to be this. All right. But now the important case is this, guys. You need to understand few things. Now here the catch involved actually. Most of the people are having issue in this part. What is this? First of all vibrations will be studied for theta to be small. Then only it is linear. And you people know if theta is small, sine theta term should be nearly equals to theta. Always we'll make these terms. Cos theta is 1, sine theta is theta. And your final equation becomes I theta double dot plus W into L by 2 into theta equals to 0. I'm just simply writing this term in a, what I can say, beautiful manner or a simplified manner. We end up with this. Now, from your previous theory, you know whatever component, what is the natural frequency of the system, guys? The natural frequency of the system is whatever coefficient you have with theta, that is WL by 2, divided by whatever coefficient you have with theta double dot. Or in other words, you ideally speaking can write in this way also. You can divide this whole expression by whatever coefficient you have here, and this equation will become something like this. And this is what is referred to as equation of motion. Now don't worry about it. The only intent as of now for this numerical is to calculate the natural frequency. And I already told you, whatever coefficient you have with theta or with x, whatever equation you have, provided that this coefficient is 1, under root of that term will give you the natural frequency. All right, so this becomes natural frequency, and this natural frequency formula is always radian per second. But now the everything changes if you know this I expression. Now I'm coming to this I explanation, and this is the whole catch of this whole lecture. If you understand this, then it is perfectly fine. So you have a rod, right? Its CG is here, which is at a distance of L by 2. Now I'm only doing I calculations. Now, first thing I want you to please by heart this. Whenever you have written this equation, I terms or all the moment terms are about hinge point. So this moment of inertia, this mass moment of inertia term, this is mass moment of inertia, not area moment of inertia. This mass moment of inertia term is about the hinge point. So you should calculate inertia about this point. But when you have a rod, all right, this you should know from the basics. I've already given you a table for this. When you have a rod about its own CG, a rod of length L and of mass M, its inertia about its own CG, mass moment of inertia, is ml square by 12. This is the basic formula. You should remember this. There is a table for this. I have already given you this table. But I don't need here. I need about the hinge point. Correct, right? So what we'll do a parallel axis theorem. We'll take this inertia, and please listen to this formula. Inertia about CG plus, now you need to shift this inertia from center point to this hinge point. So if you see, I hope most of you people can follow this. This shifting is from center of the rod to this end of the rod, and the shifting distance is L by 2. And the formula is whatever inertia you have about CG plus whatever mass you have of the rod plus whatever shift you have, not plus, whatever shift you have, square. I'll explain you this in general form in 5 minutes. Give me just 5 minutes. If you solve this, you will get this as, no, this LR same ways. You will get this as ml square by 3. So for a same rod, if you want to calculate inertia about this hinge point or the side point, the inertia will be ml square by 3. You can remember this, or we can quickly derive this. So in this particular pendulum problem, you know the natural frequency formula is given as this, where I is moment of inertia about the hinge point. So if we substitute this, I'll substitute it here. Omega n is equals to WL by 2 by I. And in place of this, W can be written as mg, length is L, 2, and I have just proved that about this point, it is ml square by 3. Correct, right? Cancel out few terms. M got cancelled out, one length got cancelled out. So omega n came out to be 3g by 2l under root for any rod of mass m, length L, hinged at its upper end. The natural frequency of the system is given as D. I know it is slightly trickier, but it is not so bad. Understand this. This is very straightforward things, which the reason of telling you these shortcuts is now anything can come in your exams, and maybe not this, another problem. Let me explain this concept in an even slightly better way. So you people have seen this. You have a hinge point about which you have hinged a rope, and there is a bob of mass m. So this is basically a point mass. So when we use a word point mass in vibration, right, what we typically want to send is says it has zero radius. All right, so it has no inertia about its own center. It's a point mass, so there is no point of talking about the center of that particular mass. So it has no inertia. Now, first thing you need to do is give a displacement. So this will go here. The displacement is theta. You know system is rotating. So I'll do one thing. I'll blindly write I theta double dot. I'll close my eyes and I'll write this. This inertia is about the hinge point. I should also remember this point. I should never forget this. Always inertia is about the point of rotation. Now, I'll do the same thing. This weight is acting downwards. There is a component W cos theta in this direction. There is a component W sine theta in this direction. And you know W cos theta will not going to create any movement. W sine theta into, now let's say this length is L. Now W sine theta into L is the movement, and I'm making it positive because this is the movement which is bringing my pendulum back to equilibrium position, and I'm not considering damping, I'm not considering any external forces. So it is free vibration, and it came out to be this. If you want to calculate natural frequency of this system, now before this, just quick note, theta is very small. So I can write it as WL theta equals to 0, correct? Natural frequency of this system, I may be going a bit fast, but I'm assuming that you people are following up this. It becomes WL by 2. And inertia, if I know my numerical is over and the unit for this is radians per second, the natural frequency of the system. But the question is, what is inertia? Now, inertia, I told you, right? Inertia of this point mass, because this is a point mass. If there is a disk of radius r, the formula is mr square by 2. I'm not discussing that. If it is a point mass, the inertia about its own CG is 0. Point mass doesn't have any mass inertia about its own point. But I don't need about its own center. I need about hinge point. So I need to take this inertia, which is 0 in this case, to this point. So I need to shift it by distance L. So plus mass of the system into the distance you are doing the shifting. See here, it was ml square by 12 here, and the shift distance was L by 2. Here your point mass is 0 and the shift distance is L. So I got formula as ml square. I'll substitute here. Omega n is equals to W I am writing as mg, L I am writing as ml square under root. I'll cancel out few terms. M got cancelled out. L got cancelled out, and you'll get the natural frequency formula as G by L under root. Just a final checking of your 10 plus 2 or what you have done in during your class 10th, 11th, and 12th. You know, time period of any quantity is 2 pi by omega n. Omega n you have calculated as this, L by G under root seconds. This we have seen a formula like 100 times during our 10 plus 12. So natural frequency, you can calculate time period and all, not we're going to do in vibrations, but I'm telling you how these things are basically done. Now, when people say a very heavy term, the last topic, guys, just 2 minutes and we are done. You have a hinge point and you have a compound pendulum. The compound pendulum is one in which you don't know the shape. You don't know what it will going to do. So let's say this is the equilibrium position, and then this compound pendulum is being deflected by angle theta. Because there is a rotation, I'll close my eyes and I'll write I theta double dot term. Now, guys, please listen to this point. All right, maybe this is, I'll draw figure. So this is the equilibrium position, and your pendulum, let's say, is here. All right, just to make you people understand, I'm drawing the better diagram. So this angle is theta. Now, because it's a compound pendulum, you don't know where the CG is lying. So let's say CG is lying somewhere. I don't know where this point is. Let's say this point is at a distance of L. Or let's say, to avoid confusion, it is at a distance of H from the hinge point. All right. Now, again, weight will act downwards. This will be W cos theta. This will be W sine theta. W cos theta will not going to create any movement about the hinge point. W sine theta, which is bringing my system back, will create a movement multiplied by H with a plus sign equals to 0. So this is restoring movement, which is bringing my system back. So if I remove, consider sine theta as small, this becomes WH theta equals to 0, and your natural frequency formula becomes W into H divided by I under root. But the catch is, what is I now? I already told you. I is nothing but moment of inertia about its own CG. You don't know now because it's a compound pendulum. You don't know what is the inertia. So people have defined a formula that about its own CG, we write it in this way, mk square. But we don't know, I'll explain this term, mk square. We don't know this. And also, I need about the hinge point. I don't need here. Whether it is 0, whether it is ml square by 12, or whether it is mk square, I'm not interested. I need inertia about the hinge point. And about hinge point, you need to shift it. Plus mass of the system and distance is h square. This I should be substituted here to get our natural frequency in radians per second. Now this K, which you are seeing here, is known as radius of gyration. So what is radius of gyration, guys? This is the radius about which your system will rotate about its own center. When you have a point mass, this radius of gyration was 0. When you were having a rod, this radius of gyration was L divided by root 12. Then only it becomes square, right? And hence, this is the point. And for disk, it becomes R by 2. R by root 2, basically. I have given a table for radius of gyration for all the systems. What I'm trying to say is, if this pendulum becomes of good shape, only this thing changes, and this shift you should remember, and you know the formulas. Everything is very much clear. The only catch involved is you should know what is inertia, how to calculate inertia, where to calculate inertia, and what are the basic formulas of inertia. That is very simple forward. It's hardly a 1-minute task of learning 4 formulas. Just to close this part, and the one point which I want to make is, let's say you have a system, something like this. You have a rod on which there is a mass m, and then this is displaced by a certain amount. So it's kind of an inverted pendulum. So when you displace this, let's say it is at angle theta, and the rotation point is this, guys. There is a hinge here. The system is rotating about this point. So I'm not solving this. I'm only doing this because to make my point. Because there is rotation, I'll blindly write I theta double dot. But now, if you see this mass, it will create two components. One will be this component and the other one will be this component. Now, if you see about the hinge point, this component will not going to create any force, so not a problem, not create any movement, not a problem. But this force, which is basically W sine theta, if you consider this W sine theta into some distance L is not bringing your system back. It will overturning your movement, right? See, your equilibrium is when it comes back. But this force is not helping you to come back. On the other hand, in these conditions, all W sine theta into L or W sine theta into H or W sine theta into L by 2, all these terms were making your system coming back. And I already told you, this is referred to as overturning movement and it should come with a negative sign. That's the only thing you should remember. And let's all other things. So this system is not possible, guys. You need to install maybe a spring here to make this system better. So I'm not going into the, so this spring will make your system better, right? So spring will come with K plus K. I'm not writing this because we'll be solving this numerical in coming lectures a lot. Pendulum arrangements with springs and pulleys and everything. The only point I want to make is what this negative sign indicates and what it is known as. So this is overturning movement. I know this is slightly catchier topic if you start from this. So I encourage you to definitely go for the vibration basics first. Understand what do you mean by natural frequency. Understand what do you mean by equations of motion. Understand what do you mean by degrees of freedom. So there is a specific way I have designed the entire syllabus. You should know what are different kind of systems. What do you mean by undamped systems, why springs are, how springs are considered, and then all these compound pendulums and simple pendulum problems should come into picture. All right, so I hope this lecture will help you. This will make your slight doubts clear and maybe some fear of rotating components will be less after this lecture. All right, so thank you so much, guys. We'll meet